On the morning of December 29th, 2025, a sequence of high-resolution images began to circulate across global astronomy networks. The first came from the LSST array in northern Chile, a telescope system designed for wide-field deep-sky scans. What it recorded looked like an error at first. The halo around 3E Atlas had grown, far beyond expected scale, brightness and symmetry. For observers who had been tracking the object since perihelion, this wasn't just an anomaly. It was something that defied almost every conventional expectation for a post-solar comet. The initial reaction from the data team was procedural. Recheck the exposure times, verify image stacking, rule out processing artifacts. But each verification passed cleanly. Nothing was wrong with the optics. Nothing had been overexposed. What they were seeing wasn't a software glitch. It was real. And then more images came in. From Hawaii, from Spain, from South Africa, from amateur telescopes equipped with narrowband filters. The object had changed, visibly, measurably, and structurally. Its coma wasn't simply larger, it was geometrically perfect. A concentric, soft bright core at the centre, surrounded by multiple glowing layers that were evenly spaced like nested shells. No turbulent motion, no collapsing gradients, just a clean radial structure extending outward at a scale over 700 times what had been measured 1 month earlier. This wasn't the behaviour of a comet ejecting gas and dust chaotically. This was ordered expansion, and it was happening fast. What startled researchers most wasn't just the size of the new halo, it was what wasn't there. Normally, when a comet expands dramatically, especially after solar heating, it does so by shedding particles. Ice vaporizes, dust gets pushed away by the solar wind, jets erupt in random directions. The resulting coma becomes diffuse, asymmetric, and noisy. It's a storm of motion, not a picture of order, but this was quiet, calm, composed. No jets, no debris fans, no flickering irregularities across the coma's surface. It held its shape. Even more unusual, the brightness remained centered. Most comets, when they expand that rapidly, fade in the middle. The dense nucleus becomes clouded by escaping volatiles, and the light spreads across the coma. But here, the central core remained the brightest point. Not blurred, not drowned in gas, focused. The symmetry was impossible to ignore. As if the halo weren't just expanding randomly, but adjusting itself. Evenly, smoothly. With precision that suggested not randomness, but regulation. To confirm what was happening, teams ran comparative overlays of December 28th and 29th images. The growth wasn't linear. It had accelerated. The coma wasn't simply getting bigger, it was doubling its radius over a span of hours. That rate of expansion, under normal comet physics, would require a violent release of energy, an explosion, a massive jet event, or fragmentation. Yet no such events had been recorded. So astronomers turned to the spectrum. What they found next only deepened the mystery. The outer edges of the coma weren't cooling. Usually, as gas escapes and radiates into space, its infrared signature drops. But here, the halo glowed evenly in the mid-IR band. That indicated a consistent energy flow, not fading out, but being sustained. And so the conclusion, while still unofficial, began to take shape. 3I Atlas wasn't disintegrating. It wasn't fragmenting, failing or burning out. It was expanding with purpose, quietly, elegantly. And whatever was driving this controlled inflation, this symmetrical growth, wasn't following any known thermodynamic or cometary model. It was something else, and it had just started. In most comet observations, the phase following perihelion, its closest pass by the Sun, is a period of slow decline. Activity flares near the heat, then dissipates. The jets reduce, the coma fades, the structure fragments, and what remains slowly drifts away, dimming over the course of days or weeks. That's how it's supposed to happen. That's what every comet in our observational records has done. Refused to follow the script. What unfolded after its perihelion event in late October wasn't a downward curve of energy. It was a flat line, steady, undisturbed, and then an upward bend. It began quietly. Observatories monitoring its infrared emissions noticed that the typical fall-off, where the object cools and becomes less active, wasn't occurring. Instead, the heat signature held firm, and over the course of 2 weeks, rather than drifting into quietude, the object stabilized. No changes in brightness, no thermal flickering, no unexpected loss of coherence. In fact, it was the stillness that became the first anomaly. Comets don't do stillness. Their internal structures are unstable. Sublimation continues well after peak heating. Dust pockets, rupture, jets rotate with spin. But 3I Atlas just held its shape, like a structure with internal damping, absorbing thermal pressure without releasing stress. And then came the expansion. Around mid-December, the coma began to grow. Not suddenly, not explosively, but incrementally, step by step in concentric controlled layers. It wasn't a dust plume, it wasn't a flare, it was a progression, as if something had stabilized and was now unfolding. What made the observation even more unusual was how clean the geometry remained during that expansion. The growing halo didn't blur or break at the edges. It stayed symmetrical, centered, uniform. Astronomers started to notice a pattern in the brightness layers too. The coma wasn't just growing spatially, it was layering light at specific intervals, brighter in near ultraviolet, then fainter in mid-infrared, then another bump in visible light. The gradients pulsed outward in timed increments, forming what looked almost like nested shells of luminescence, not chaotic diffusion, sequenced bands of activity. And with every new layer, the outer boundary of the coma increased at a faster rate. The growth was accelerating. This was the moment that solar physicists joined the discussion. They proposed a theory. Perhaps the expansion wasn't being driven from the interior at all, but rather by absorption of external particles, solar ions, wind-blown electrons, or remnant radiation pressure. Could 3I Atlas be passively feeding off the electromagnetic turbulence left behind in its wake? That model had some merit. The comet had recently passed through a region of enhanced solar flux. But the issue wasn't energy availability, it was precision. The outer layers weren't dissipating like vapor clouds. They were holding shape, regulating distance from the nucleus, and radiating in harmonics. This wasn't passive accretion, it was active structuring. Another possibility arose. Maybe 3I Atlas wasn't, shedding mass but repositioning it. An internal redistribution model, one in which volatiles or charged dust particles were being relocated, not ejected, via electromagnetic alignment or rotational redistribution. In short, the object wasn't dying, it was reconfiguring. And what made the idea plausible was the data's consistency. No spike in gas emissions, no volatile signatures from deep core rupture, no explosive energy loss. Instead, the light curves were stable. The rotation profile showed no tumbling. The coma's motion aligned with the object's core. Every parameter, from angle to luminosity to mass conservation, pointed toward a system that was not only holding together, but executing a plan. This is when the term transition phase entered the language of the analysts. 3I Atlas, they now believed, had moved from its solar stabilization state into a new phase, expansion, not due to collapse, not due to thermal breakdown, but something else entirely. By the time the full dataset from December 29th was compiled, the numbers were no longer subtle. The observed expansion of 3I Atlas's coma had crossed a threshold that forced analysts to stop using comparative language altogether. This was no longer a question of larger than expected. It was mathematically disproportionate. Measurements taken from stacked optical and infrared frames showed that the visible envelope surrounding the nucleus had expanded to more than 760 times its previously measured apparent volume since late October. Not its brightness, not its mass, its spatial footprint. That distinction matters. In typical cometary behavior, when a coma grows rapidly, it does so because material is being violently expelled. Dust and gas scatter outward, thinning as they go. The result is expansion paired with dilution. But here, dilution wasn't happening. Surface brightness across the expanding halo remained nearly constant. In some bands, it even increased slightly. This created an immediate contradiction. To expand that much, something had to be driving material outward. But to remain that coherent, something also had to be maintaining structure. Those two conditions rarely coexist in natural outgassing events. One favours chaos, the other demands control. When analysts attempted to reconcile the data using standard sublimation models, the equations collapsed. The estimated amount of material required to sustain a coma of that size, without losing luminosity, exceeded the maximum plausible volatile inventory of an object this size. Even if 3I Atlas were composed almost entirely of carbon dioxide ice, the mass loss required would have been unmistakable. But no corresponding depletion was observed. The nucleus brightness remained steady. Its spectral signature showed no abrupt drop in volatiles. And its rotational behavior didn't change. In other words, the object appeared to be expanding without paying the usual energetic cost. This is where researchers began to reframe the problem. What if the growth wasn't a result of mass loss at all? What if the coma wasn't simply material escaping, but material being organized? Some proposed that charged particles from the solar wind were being captured and trapped within a structured electromagnetic field around the object. Others suggested that ionized gases released earlier in the encounter were being held in place by magnetic confinement, rather than dispersing into space. Both ideas were controversial. Neither had precedent in known cometary physics. But they explained something critical: how volume could increase without corresponding loss. The growth curve itself offered another clue. It wasn't smooth, it wasn't exponential, it advanced in steps. Over the course of December, observers recorded intervals where the expansion paused, stabilized, then resumed, each time at a higher baseline. These plateaus lasted hours, sometimes longer. Then the halo would push outward again, evenly, like a boundary being reset. This behavior looked less like evaporation and more like deployment. By now, the language in internal discussions had shifted. Words like outburst and flare quietly disappeared. They were replaced by terms like phase change and structural transition and envelope formation. Because what 3I Atlas was doing no longer resembled disintegration. It resembled growth. While the outer halo of 3I Atlas continued to expand, another detail became impossible to ignore. The core wasn't moving. In normal comet dynamics, increased activity introduces instability. Jets create torque. Uneven heating alters spin. As material escapes, the nucleus begins to wobble or tumble, often unpredictably. This rotational chaos is one of the most reliable indicators of internal stress. But here, there was none. High-cadence photometric monitoring showed that the nucleus of 3I Atlas maintained a stable rotational signature across weeks of observation. No acceleration, no deceleration, no precession, no jitter. It behaved like a system with internal balance. This was deeply unsettling to dynamicists. If the object were actively expelling material to drive expansion, conservation laws demand a response. Thrust in one direction produces rotation or countermotion in another. Yet the nucleus behaved as though it were isolated from the activity around it, as if whatever was happening in the coma wasn't mechanically coupled to the core. Some researchers described it as decoupled. Others used a more evocative phrase, anchored. The center of 3I Atlas acted like the fixed hub of a growing structure. Thermal data reinforced this picture. Despite the increase in radiative output from the expanding envelope, the core temperature remained stable. No overheating, no cooling, no thermal runaway. The nucleus neither absorbed nor shed energy in proportion to the activity surrounding it. This implies regulation, not passive. Insulation, but active equilibrium. One hypothesis suggested that the nucleus may be surrounded by a boundary layer, an interface that mediates energy transfer between core and coma. Such a layer could theoretically absorb mechanical stress, redistribute charge, and damp rotational forces. In engineered systems, this would be called a stabilizer. In natural bodies, it doesn't exist. Yet the data suggested something was preventing the expansion from disturbing the core. Even more curious was the alignment. The expanding coma maintained a constant orientation relative to the object's trajectory. As 3I Atlas moved through space, the envelope didn't lag behind or distort under solar pressure. It stayed centered, balanced, symmetrical. This isn't how free-floating gas behaves, it's how a field behaves. By the end of December the 29th, one conclusion had become unavoidable among those studying the object closely. Whatever 3I Atlas was doing, it wasn't losing control, it wasn't fragmenting, it wasn't reacting, it was maintaining stability while expanding, a combination that suggests not breakdown, but design-level coherence. And that realization set the stage for the next question. If the core isn't driving the expansion, then what is? As the coma of 3I Atlas continued to grow outward in symmetrical layers, scientists began turning their attention inward, to the frequencies of light that filled the space between the nucleus and the edge of the halo. It was here, in the spectral data, that something even stranger was beginning to appear. Infrared and ultraviolet observatories began detecting emission lines that didn't match the timing or intensities of previous cometary events. These weren't new gases being added to the spectrum. They were familiar molecules, carbon dioxide, carbon monoxide, and traces of hydroxyl radicals. But they were behaving in a way that no comet's gases ever had before. The spectral lines weren't fluctuating randomly. They were shifting in unison. This phenomenon, known as spectral coherence, is exceedingly rare in naturally expanding gas clouds. Normally, when ice sublimates from a comet's nucleus, the resulting gases disperse outward in unpredictable directions, colliding with solar wind, fragmenting under radiation, and stretching across space in uneven densities. The emission lines from these gases typically show broadening, evidence of turbulence, thermal agitation, and Doppler shifts caused by particles moving at inconsistent speeds. But in the coma of 3I Atlas, something else was happening. Over a period of 6 hours on December 29th, a repeating pattern emerged. Spectral lines would narrow, pulse, then drift slightly, all in synchronized intervals across multiple sensors. Telescopes in South Africa, Australia, and Hawaii all recorded the same modulation. This wasn't just a shift in brightness, it was a shift in behavior. The pattern resembled a wave, not a thermal wave driven by heat, but a coordinated optical resonance, like a bell being struck not once but repeatedly at near-perfect intervals. One observer described it as watching a field of gas breathe, and then came the unexpected twist. The coherence wasn't coming from the core, it was originating from halfway between the nucleus and the outer halo, roughly midway into the expanding coma. The location made no sense. There was no heat source at that position, no detected mass, nothing that would produce synchronized behavior, so what was causing it? One theory suggested the presence of ionized filaments, thin strands of charged particles embedded in the coma that were resonating with ambient electromagnetic fluctuations. These filaments, if aligned correctly, could serve as waveguides, creating feedback loops of low-frequency light and plasma interaction. Another possibility was even more unorthodox, that the coma itself had formed a temporary shell-like structure capable of reflecting or amplifying radiation in confined zones. This was supported by subtle polarization measurements that indicated light wasn't just passing through the coma, it was being reflected within it, like a lens or a cavity. Engineers studying the phenomenon compared it to a laser resonator, two mirrored surfaces that trap light between them, bouncing photons back and forth until a harmonic frequency builds. Of course, nothing in the coma of 3I Atlas resembled mirrors, but if the density gradients were steep enough and if the gas had aligned along magnetic seams, then localized reflection was theoretically possible. The implications were staggering. A comet behaving like an optical resonator? A gas envelope synchronizing its emissions across vast distances without any mechanical connection? That didn't resemble disintegration. It resembled orchestration. By the end of the day, the spectral analysis teams were no longer talking about passive chemistry. They were talking about behavior. Something inside the coma wasn't just responding to sunlight, it was responding to itself. In the weeks following perihelion, astronomers kept expecting a moment that never came. That moment, familiar to anyone who studied cometary behavior, is fragmentation. It's the inevitable result of stress. Thermal gradients building across the nucleus, pockets of gas pressurizing beneath the surface, cracks spreading like spiderwebs through volatile-rich regions. And eventually the structure gives. A piece breaks off, a tail splits, a dust arc fans into space. But with 3I Atlas, that moment never arrived. Across all wavelengths, optical, infrared, ultraviolet, there was not a single signature of mass separation. No asymmetrical tails, no debris flares, no differential motion between the coma and the core, and this wasn't for lack of observation. The object was being tracked by more than 40 telescopes globally. Every major solar system monitoring agency, from NASA's JPL to ESA's heliophysics team, had assigned personnel to analyze data in near real time. Dozens of amateur astronomers with high-end gear had joined the effort as well, scanning the coma nightly for dust fans or trailing fragments. Still, the shape remained stable. The coma's radial symmetry never broke, its outer shell never rippled. Even during spikes in solar wind activity, when increased radiation pressure might have exposed internal weaknesses, the structure held. The stability itself became a red flag. No known comet of this size and volatility ratio had ever passed this close to the Sun and remained completely intact for this long. The statistical likelihood of surviving that encounter without so much as a visible crack is vanishingly small, so either 3I Atlas was an extreme outlier, or it was doing something fundamentally different. Internal models attempted to simulate what kind of structural strength would be required to resist fragmentation under those conditions. The answer? A nucleus with cohesion at least 5 times stronger than any observed natural comet. Some researchers proposed exotic mineral bonding, an unusually dense matrix of carbonaceous material or interstellar silicates forged in colder, higher pressure environments. But others found that explanation lacking. Even with superior cohesion, comets still fragment due to tidal forces and uneven outgassing. 3I Atlas had experienced both, and yet it had responded with expansion instead of fracture. The anti-fragmentation became part of the mystery. If this object wasn't shedding pieces to relieve pressure, how was it dissipating energy? The answer, once again, pointed back to the coma. Rather than breaking open, the object seemed to be redirecting its internal activity outward into organized jets and symmetric light patterns. Energy wasn't exploding, it was diffusing, smoothly, deliberately. Some scientists called this graceful venting, others described it as pressure, shedding without trauma. And that phrase captured what made 3I Atlas so unusual. It wasn't surviving by accident. It was managing stress like a closed-loop system, not resisting collapse, but avoiding it entirely through regulation. By late December, there was consensus among observers. Fragmentation was no longer expected. Not because the object was too far out to break, but because it wasn't built to break. It had passed through the heat, it had absorbed the pressure, and instead of cracking, it had expanded in silence. The most destructive forces in the solar system had failed to tear it apart. And that meant something new was happening. Not a comet falling apart, but something else, something stranger coming together. As December drew to a close, what had initially been a curiosity, an unusually stable cometary coma, began to transform into something far more compelling. The expansion was undeniable, the symmetry persistent, the lack of fragmentation impossible to ignore. But now, for the first time, the glow itself was pulsing. It was first noticed by amateur radio astronomers operating low-frequency receivers in South Africa and northern Canada. Their instruments had been scanning the general region of 3I Atlas primarily to monitor cosmic background noise and auroral echoes, but what they captured instead was unexpected. A repeating signal in the ultra-low frequency range. It wasn't a voice, not a beacon. Nothing artificial in the sense of modulation or message. It was a harmonic. A repeating pulse at exactly 3.2 Hz. To the untrained ear, that frequency might seem unremarkable, but in deep space radio, especially in passive reflection studies, such regularity is rare. Most space noise is stochastic, caused by cosmic rays, magnetic reconnection events, or high-energy plasma interactions. The emissions fluctuate, they decay, they spread across frequencies, but this pulse didn't drift. It stayed locked at 3.2 Hz, slow, rhythmic, and consistent. It also didn't match any known source, no nearby satellites, no ground-based interference, no pulsars, quasars, or solar processes matched the rhythm or direction of origin. It was coming from the coma of 3I Atlas, and most importantly, it was synchronized with light. Simultaneously, telescopes in Spain and Chile recorded periodic dimming and brightening in the outer shell of the comet's coma. Not random flickers, not caused by turbulence, but slow, deliberate oscillations in brightness, peaking and falling in rhythm. At first, these fluctuations were dismissed as atmospheric noise, but then more observatories confirmed them, some using adaptive optics, others via filtered photometry. The timing matched the radio pulses exactly. A 3.2 Hz signal, a 3.2 Hz glow. This was no longer just an expanding coma, it was a system with periodicity. The physics community refers to this as coherent modulation. It's typically seen in engineered systems, radar arrays, resonant chambers, harmonic dampers. But here it was, happening naturally, in the coma of an interstellar object that had already defied expectations at every turn. Some theories emerged quickly. One group suggested that the particles in the coma were aligning electrostatically, forming ordered structures that resonated in response to ambient solar wind. Essentially, the coma had become a loosely bound electromagnetic cavity, oscillating at a frequency determined by its size, charge density, and shape. Others considered acoustic modes. Plasma can carry waves, and if the coma density were just right, those waves might establish standing resonances, similar to how sound bounces in a tunnel or between canyon walls. But this theory struggled to explain the pulse's precision and why it would remain so stable despite the object's movement and solar interactions. There was also a darker theory, one not widely published but whispered in closed forums. What if the pulse wasn't a product of interaction at all? What if it was a signature of internal behavior, a self-generated rhythm, the timing mechanism of something operating in cycles? Of course, that's speculation, but the data was now clear. 3i Atlas wasn't just glowing. It was pulsing, not chaotically, not randomly, but precisely, every 312 milliseconds, and whatever was causing it had not yet changed frequency, not even once. The tails of comets are well understood, at least they used to be. There are typically two: the dust tail, made of fine particles pushed away from the comet by sunlight, and the ion tail, formed from charged gases that react to solar wind. These tails always point away from the sun, not because of momentum but because of pressure, photon pressure, and magnetic field alignment. The tails bend, twist, and scatter. They're beautiful, but they're also predictable. So when observers began noticing something forming in the opposite direction, pointing back toward the sun, it triggered immediate debate. At first, the phenomenon was subtle, a thin, narrow line of light that looked like an artifact, a smudge in the telescope optics or a faint optical illusion created by Earth's viewing angle. Astronomers called it an anti-tail, a visual effect, not a real structure. It happens when dust particles previously shed from the comet linger in space, forming a false shape that, from our vantage point, appears to point sunward. But with 3i Atlas, the anti-tail wasn't fading. It was growing, and by December 29th it wasn't just visible, it had become symmetrical, matching the primary tail in length, in brightness, and, strangely, in structure. This changed everything, because anti-tails are not supposed to develop mass. They are by definition illusions. Yet this one wasn't static. It was behaving dynamically, responding to solar wind in ways that suggested it was made of the same material as the ion tail. Researchers attempted to model the trajectory of dust particles that could produce such an effect. The numbers didn't fit. The required geometry was impossible unless the comet had expelled material directly toward the sun, and had continued to do so over several days. But comets don't eject matter toward the sun. The physics don't allow it, unless something is doing the opposite of normal, unless something is using sunward ejection deliberately, as thrust. The speculation returned quickly to propulsion dynamics. If you were to design a basic maneuver in space, you'd eject material in the opposite direction you wish to travel. Expel mass sunward, you move anti-sunward. Expel mass backward, you accelerate forward. And 3i Atlas, despite lacking observable spin-up or visible jets, was shifting. Slightly, cleanly. Its trajectory had curved off its expected hyperbolic arc, just enough to raise eyebrows, but not enough to cause alarm. Until now. Now there was a tail forming toward the sun, not curved, not wispy, but focused, like a thin counter-thrust vector. The symmetry of the system began to draw comparisons to bidirectional engines, systems that maintain balance by emitting material in both directions. Some spacecraft use this technique during station keeping or orbital alignment. And now, deep in space, an interstellar object appeared to be doing the same. Was it natural? Possibly. There could be a volatile trapped on the sun-facing side of the object, a pocket of gas slowly venting backward. But even then, the pressure should push the tail away, not toward. So observers returned to the geometry. They mapped the direction of both tails, They found alignment. The ion tail pointed directly away from the sun. The anti-tail pointed directly at it. The structure was symmetrical, active, coherent. Whatever was happening inside 3i Atlas, it wasn't drifting. It was directing. And the skies were watching, quietly, carefully, as the object pointed not just away, but also straight back at the source of its ignition. By the morning of December 29th, something strange began to appear in the high-resolution composite imaging pulled from several observatories. Along the lateral edges of 3i Atlas, what had once been faint ridges of material, thought to be loosely bound surface dust or fragmented cometary jets, were now growing into pronounced vein-like structures. They weren't just expanding in volume, they were organizing. Observers described them as ribs that curled outward, forming symmetrical extensions across its midsection and trailing off like arterial branches. But what disturbed researchers wasn't the visual pattern itself. It was what those structures were doing to the solar radiation that passed through them. Instruments like the SOHO satellite's LASCO C2 filter began registering odd refractive distortions as sunlight moved past the object. Instead of light scattering randomly, as it does with most ice dust comets, the material inside these, expanding veins appeared to redirect it in controlled arcs, almost like miniature prisms or lenses. Heliophysicists struggled to explain it. The temperature at that distance from the sun shouldn't be causing this kind of organized mineral bloom, nor should solar wind fluctuations alone be strong enough to shape it so uniformly. One theory proposed that the material being ejected wasn't merely being lost to space, it was looping back, forming self-reinforcing filaments that reattached to the object's structure like scaffolding. If that was the case, it meant the growth wasn't just passive, it was dynamic, a system reacting to its own expansion. The implications were enormous. A comet forming controlled scaffolds would have to possess internal stabilizers, or an underlying field, that allowed its growing pieces to remain magnetically or gravitationally bound. No natural object in known solar history had demonstrated this, and if 3i Atlas was showing it now, then the term comet may no longer be enough. These expanding ribs began to affect other readings too. Polarization data, used to measure how light waves shift as they bounce off surfaces, began to diverge from all previous Atlas data. The directionality of the reflected light suggested that the surface was no longer random dust and rock. It was aligning, reflecting in unison, as though the body was developing facets, like armor. Across several academic circles, including closed research threads at Caltech, the working terminology began to shift. Observers stopped calling the object a comet-like body, and started referring to it as an expanding anomalous structure. But there was still more to come, because within those veins, those newly forming arms of translucent matter, instruments began detecting something else. Faint pulses, not thermal, not magnetic, not radiative in the conventional sense, but rhythm. Each segment, each arc, each mirrored branch of 3i Atlas's growing frame was flickering. Not in random bursts, but in regular, repeatable intervals, and those intervals matched something already recorded earlier in its journey, the 3.3 Hz hum seen during its approach to the sun weeks before. This time, however, the rhythm wasn't isolated to one tail or jet, it was radiating from multiple points, evenly spaced across its growing shell, as if the object wasn't just expanding in size, it was synchronizing, and now it was broadcasting that synchronization outward, across vacuum, across magnetic fields, across entire AU distances. The expansion was no longer just a physical phenomenon, it was a signal. As twilight crossed over ground-based observatories from Chile to South Africa, a new set of spectral readings forced several teams into overnight lockdown. While the visual and radar images of 3i Atlas remained mostly consistent with the previous 12-hour cycle, there was now a second curve appearing in deep, ultraviolet analysis, not a flare, not an echo, but a shell, ghostly, symmetrical, and encasing the object entirely. At first it was assumed to be interference, a data reflection. But once it appeared across multiple observatories using unrelated hardware and processing stacks, the odds of a glitch collapsed. This was real, and it had structure. Roughly 3 times the width of the already massive 3i Atlas core, this translucent shell displayed several impossible characteristics. First, its boundary wasn't fuzzy, as most outgassing clouds would be. It was sharp, cleanly defined at the edges, like a bubble made of energy rather than matter. Second, it was spinning. Not in the same direction as the object's core, but counter to it. The outer shell rotated in reverse at roughly 1/3 the speed of the body within. That rotation wasn't just aesthetic, it was interacting with the solar wind, bending plasma flow around itself instead of allowing it to pass through. Third, the shell was semi-permeable. Radar pulses from Earth's dish arrays showed that some frequencies were absorbed entirely, while others passed through unaffected. This wasn't absorption based on material density, it was frequency selective, as if the shell knew what to let in and what to block. Experts on exospheres and magnetospheres were baffled. This wasn't behavior associated with cometary halos, or even the extended coronas of active stars. The shell didn't ionize surrounding gas, it didn't decay or degrade like dust clouds do, it simply stayed. More disturbingly, its appearance wasn't triggered by solar proximity. It had happened farther out, after the object had already begun accelerating again on its approach to Jupiter. Some began to hypothesize that the first expansion, the visible growth of the core and its veins, was only a prelude. That whatever 3 Atlas was doing internally, the result was now manifesting as an external defense, or perhaps even an envelope designed for atmospheric transition. If Jupiter had an atmosphere dense enough to require an external buffer, this could be that buffer forming in real time. But others weren't so sure. One European researcher noted that the shell's inner boundary pulsed faintly every few hours, not randomly, but on a timer. Those pulses were low-amplitude reflections of the internal hum. It was as if the shell wasn't just surrounding the object, it was listening to it. And now the entire construct, object and field, core and shell, was behaving like a unit, a vessel, not just growing, not just adapting, but preparing. And whatever it was preparing for, it had just entered Jupiter's gravitational influence. As 3I Atlas moved closer to Jupiter's orbit, something remarkable began to occur. Not in the comet's tail or visible emissions, but within the field lines of Jupiter's massive magnetosphere. For days, radio telescopes tracking the planet's auroral bursts noticed slight irregularities. At first they were subtle, barely a deviation from background noise, but the rhythm of these pulses began to match something else, something inbound. Jupiter's magnetic field is the strongest in the solar system, capable of generating its own radiation belts and shaping plasma waves across its moons. When anything approaches Jupiter, it interacts with this immense field, sometimes visibly, sometimes invisibly. But with 3I Atlas, the interaction didn't look like disturbance. It looked like harmony. The closer it came, the more synchronized the signal patterns became. As if the comet wasn't just reacting to the field, it was anticipating it. Plasma physicists called it sympathetic resonance, like 2 tuning forks on opposite sides of a room vibrating together without touching. The energy from Jupiter wasn't overwhelming the comet. Instead, 3I Atlas began oscillating at the same frequency. Every few minutes, radio instruments would pick up matched pulses, one from Jupiter, one from Atlas. This wasn't just electromagnetic echo. The comet's mass, still ballooning at an inexplicable rate, began aligning its position to these energetic nodes. It was drifting, not randomly, but toward regions of maximum field amplitude, almost like a sail-catching wind, except here the wind was magnetic, and this was no passive glide. Observatories noted that the comet wasn't simply being drawn in, it was shaping its own arc, like a vessel steering through invisible currents. If it was natural, it was one of the most elegant magnetic dances ever witnessed in space. If it was intentional, it meant we were looking at something that understood field harmonics well enough to exploit them. No space agency issued a statement. But deep inside mission logs, the terminology changed. 3I Atlas was no longer labelled as a passive object. It had become a dynamic participant, and Jupiter, with all its chaos, now served as a stage, one where the comet's behaviour shifted from bizarre to calculated. While attention remained focused on Jupiter and the growing mass of 3I Atlas, a quiet anomaly unfolded near one of the gas giant's most mysterious moons, Callisto. Known for its heavily cratered surface and minimal geological activity, Callisto had always been considered the most quiet of the Jovian moons. No subsurface ocean like Europa, no volcanic eruptions like Io. Just a cold, still world on the edge of Jupiter's influence. But then Callisto blinked. It began with a single light curve anomaly. A flash, so brief it was almost discarded as sensor noise, registered by an orbital telescope focused on Jupiter's limb. The anomaly repeated precisely 6 hours later, and again in the same spot. Scientists at first assumed it might be a reflective surface, a transient albedo spike caused by an ice patch facing the sun. But when the pattern held and the pulses continued, identical in duration, spacing, and wavelength, new questions arose. The light was not a reflection. It had a frequency profile unlike any geological process. Some even compared it to artificial laser bursts, but they were weak, almost whisper level in intensity, more of a ping than a flare. Then came the triangulation. Cross-analysis from 2 deep space observatories confirmed the source, a precise spot near Callisto's equator, a crater known as Arcus Basin. That area had never shown any activity. No outgassing, no tectonics, nothing unusual. Yet now, it pulsed. The most disturbing part wasn't the pulse itself. It was what happened in the moments after each flash. The surrounding magnetosphere, normally turbulent due to Jupiter's emissions, would stabilize, briefly, just for seconds, as if the light event was resetting something. This wasn't consistent with natural behavior. The hypothesis that emerged was deeply unsettling. The pulses might not be light emissions at all, but corrections, targeted, disruptions meant to modify Jupiter's field or test Callisto's interaction with it. And each pulse, each blink, occurred within minutes of new mass increases in 3I Atlas. It was as if Callisto had become a signal relay, a calibration node, a moon with no atmosphere, no geologic activity, suddenly blinking in rhythm with a comet that had grown 760 times its size and was still steering through the solar system like it knew where it was going. It was never just the tail, nor just the brightness. What changed everything was the shape. Not the vague, dusty outline that comets often display from a distance, but the dense interior contour that spaceborne instruments finally locked onto. As 3I Atlas drew farther from Earth and closer toward the deeper gravitational influence of Jupiter, a new opportunity emerged. With Earth's scattering field behind it, and the Sun no longer interfering with reflection patterns, long baseline interferometers began to resolve deeper spatial characteristics. They weren't looking at the light anymore. They were looking at the signal delay, how different bands of emission arrived across a known span of antennas, and from that signal pattern, one strange detail emerged. 3I Atlas wasn't smooth. The central mass wasn't round, bulbous, or spheroidal like most cometary nuclei. It exhibited angularity, subtle ridges, repeating corners, and flat reflective behaviors that hinted at geometry, not erosion. This wasn't the jagged randomness of an ancient frozen rock. These patterns repeated, not perfectly but rhythmically. One sector showed a hexagonal bend, another cornered at an incline matching nearly 30 degrees before vanishing into shadow, and the data was consistent across multiple observatories. The core had planes, not curves. For days, analysts attempted to dismiss it as artifact interference, aliasing from overlapping plasma wakes. But the waveform residuals didn't lie. These shapes weren't optical, illusions or guesswork based on fuzzy pixels. They were phase-aligned reflections, meaning that something hard was bouncing electromagnetic signals in a precise way. When infrared returns were layered atop magnetic readings, the case only deepened. The temperature profile of the nucleus was not uniform. You'd expect one side to cool while the other warmed, standard thermal flux from sunlight rotation, but instead, thermal heat lines formed stripes, not gradual fades, but sharp-edged contrast zones, like tiles. The immediate hypothesis was composition. Perhaps differing materials responded to solar heat at different rates. But even that couldn't account for the spacing. The separation between each thermal zone followed a spacing too consistent to be random, almost grid-like in periodicity. And that's when the phrase was first uttered aloud on a private NASA JPL call. Modular segmentation. It was said softly, hesitantly, but once it left someone's lips, it couldn't be unsaid. What if the core of 3I Atlas wasn't just shaped strangely? What if it was constructed? This idea, of course, clashed with every pre-existing comet model. No mission to date had found internal symmetry at this scale. Not in Halley, not in Tempel 1, and certainly not in Oumuamua. Even interstellar objects showed signs of violent formation, not designed modularity. Still, the reflections kept repeating. The thermal stripes held their sharp edges, and the deeper 3I Atlas moved toward Jupiter's influence, the more clearly those shapes became. It wasn't smooth, it wasn't eroded, it was shaped, and possibly sectioned. Not naturally, but intentionally. The moment 3I Atlas entered Jupiter's deep field, the region of strong gravitational shaping known to curved space itself, everything accelerated. Not just its trajectory, but its effects. Scientists had long studied how massive planets like Jupiter act as gravitational lenses when light or radiation passes nearby. It bends, a cosmic mirror of sorts. But what caught researchers off guard was how precisely 3I Atlas began to react to this curve. It didn't wobble, it didn't tumble chaotically like most icy bodies nearing a gas giant. Instead, its orientation corrected, as if responding to the tidal distortions not with resistance but with intent. The object seemed to stabilize, almost hover, in relation to the incoming gravitational waves. Multiple gravitational interferometers, both Earth-based and satellite-linked, detected the same thing: small but consistent phase locks between Jupiter's oscillating influence and the structural rhythm of 3I Atlas. Imagine a tightrope walker adjusting to the sway of the rope. But instead of swaying, 3I Atlas adjusted before the pull came, like it was predicting each distortion. Even stranger, the inner magnetic sheath surrounding its plasma halo thickened, not thinned, under Jupiter's pull, as though the object had reinforced itself, bracing against the distortive force not with fragility, but with calibration. And then the emissions began. Jupiter, famous for its own massive auroras and radio storms, began to flash bursts of low-frequency noise not originating from its poles, but from its equatorial band, something that hadn't been seen since Juno's early orbits. These pulses matched the rotational pacing of 3I Atlas's core, a rhythm established days prior during its growth phase. The implication, a harmonic resonance. In simpler terms, 3I Atlas was not just entering Jupiter's space, it was interacting with it, and possibly tuning to it. Then came the visual confirmations. Spectrographic overlays from telescopes in Hawaii and Chile showed a brief lensing flare, a visible bulge in background starlight, not from Jupiter itself, but from the region around 3I Atlas. The object had become massive enough, or structured enough, to bend light. Not a gravitational lens in the traditional sense, but a focused distortion. Its halo swelled, its anti-tail sharpened, and the angular reflections from its core became mirror-like. A cosmic mirror, aligned not randomly but with celestial precision, toward Jupiter, and toward Earth's orbital plane. For mission analysts at ESA and the Deep Space Network, this moment triggered a classification shift. 3I Atlas was no longer being logged as a comet. Its status was updated internally, not made public, to something else, a term rarely used. Adaptive structure. This wasn't poetic, it wasn't dramatic, it was a placeholder. A word used when natural models no longer suffice, but certainty remains out of reach. The gravitational mirror of Jupiter didn't just reveal 3I Atlas's shape, it revealed something deeper. It was responding. When 3I Atlas crossed the outer threshold of Jupiter's magnetosphere, it wasn't just another moment in space navigation, it was a confrontation between two colossal forces. One, a massive planetary field forged by rotation and internal metallic hydrogen. The other, a cosmic anomaly that had defied prediction since the moment it arrived. Scientists monitoring the encounter didn't expect harmony, but what they got was stranger than any prior forecast. Instead of turbulence, there was resonance. Jupiter's magnetosphere isn't silent. It sings through radio waves, auroral pulses, and charged particle storms. Spacecraft like Juno have long recorded its chaotic rhythms. But as Atlas entered its grip, something began to change. A subtle hum began to layer across the native emissions. Not overpowering, not intrusive, just tuned, matched, like two instruments syncing in key. Deep frequency analysis showed this wasn't interference, it was alignment. The pulses from Atlas, already mysterious on their own, began matching the rhythm of Jupiter's magnetotail, not lagging behind, not echoing, but perfectly in step. And that was a problem, because nothing natural should be able to predict or adapt to Jupiter's fluctuating magnetosphere in real time. Theories flooded in. Some suggested Atlas was acting as a resonator, passively vibrating in sympathy with the surrounding plasma fields. Others weren't so sure. They pointed to the pacing of the pulses, the mathematical consistency, the suggestion of a system adapting rather than responding. If it was just a comet, why was it responding as if it understood the environment? And then came the auroral scatter. Jupiter's polar lights are the largest in the solar system, towering atmospheric storms of charged particles drawn into the poles. But after Atlas aligned its trajectory along the outer lobe of the magnetosphere, the auroras twisted, not randomly, not like typical solar interference. The bands elongated, split, then reformed into mirrored arcs, and within them, a pattern. Data overlays from Earth-based telescopes revealed repeated ripples, exact intervals, recurring phase modulations, as if a code were being broadcast through the auroral shell. The same pattern appeared 3 rotations later at a slightly higher latitude, and again and again. The recurrence had no solar origin. It wasn't from Io or Ganymede or any known magnetic satellite interaction. This was coming from the alignment zone. The scientific consensus broke into 2 camps. One group believed the resonance was natural, an effect of mass, magnetism and timing. But others, looking deeper at the structured nature of the emissions, began to whisper what no one wanted to say. That maybe Atlas wasn't adapting. Maybe it was tuning in, and not for the first time. While magnetometers and radio telescopes struggled to make sense of the electromagnetic pulses between 3i Atlas and Jupiter, another set of instruments quietly began collecting their own kind of signal, one that couldn't be mistaken for interference. Heat. The infrared arrays stationed at Mauna Kea, the VLT in Chile, and ESA's deep sky platforms all registered a slow but unmistakable rise in Atlas's thermal output. This wasn't surprising at first. A body moving closer to the Sun, or interacting with charged environments, would naturally experience some warming. But this wasn't surface melting. It wasn't a tail flaring from solar heating. It was controlled zonal increase. Specific bands of the object's surface began to glow in infrared, a signature that suggested active directional heat management. On natural bodies like asteroids or comets, thermal radiation disperses unevenly but predictably. Rotational gradients, sun-facing flares, tail emissions. What these arrays picked up was something altogether different. Concentric rings, not physical rings, but heat bands, like ripples across a drumhead. They pulsed in sequences, rising, fading, and then returning in intervals spaced nearly precisely by time, not by position. It was as if something beneath the surface was breathing. NASA's thermal models broke. None of them could replicate the readings without inserting one unthinkable variable: internal regulation. That's when the older records were pulled. Not of Atlas, but of interstellar objects past. Oumuamua, Borisov, even long-dormant relics like Halley's Comet during its anomalous 1986 pass. Some of these had shown unusual heat signatures, yes, but nothing on this level, not with such patterned emission, not with this kind of repeatable thermal loop. The term infrared echo began appearing in internal discussions. The idea was simple. What if Atlas wasn't just radiating heat, but returning it? As if the thermal increase was happening, then bouncing off a subsurface layer and returning slightly delayed. If this were true, it would imply structured interior geometry. Layers, cavities, perhaps even reflective surfaces or insulated cores. That changed everything. If Atlas had an inner structure complex enough to create timed thermal echoes, then it wasn't a typical comet. It wasn't even debris. It was a system. And then came the spectrograph reveal. The emission wasn't just heat. Within the infrared spectrum, analysts found something else. A repeating spectral dip consistent with thermal regulation materials. Not common rock, not ice, but compounds resembling carbon fiber matrices, lab-based analogues used in aerospace insulation. The implications were staggering, because such patterns don't form naturally. And their heat retention behaviors matched nothing seen in celestial records. The only explanation: the object was managing its own energy flow, and that led to a single question. whispered in the back channels of astrophysical communities around the world, if Atlas is regulating heat, what's generating it? It began with a subtle deviation, one that no one expected. For weeks, 3i Atlas had carved a perfectly predictable plasma wake behind it, shaped by solar-wind interactions and its own energetic outflows. But on December 29th, that wake didn't just widen, it inverted. The plasma flow, once trailing neatly behind the object, began bending forward, toward its direction of motion, almost as if the tail wanted to lead the comet instead of follow it. Scientists were quick to check for solar wind fluctuations or magnetic turbulence, but none of the usual suspects applied. The solar environment was calm, the wind was stable, and yet 3i Atlas was exhibiting a phenomenon so rare it didn't have a confirmed classification. What could force a plasma tail to reverse orientation? Some suggested that a newly energized magnetic field near the nucleus was realigning charged particles. Others proposed a shielding effect, like a bubble forming ahead of the object that deflected charged particles forward, creating a mirror effect. But both explanations struggled under scrutiny. The direction of the reversal was too clean, too coherent, and the symmetry of the arc didn't match any known reactive field structure. The ESA's Solar Plasma Lab proposed a theory no one expected to hear out loud. 3i Atlas wasn't just reacting to solar wind, it was modulating it. The tail was not just a byproduct of ion interaction, it was directional, possibly even designed. That claim alone stirred immediate controversy. Directionality in plasma emissions isn't unheard of in natural bodies, but when coupled with synchronization patterns, field layering, and frequency harmonics, as seen in earlier chapters of 3i Atlas's journey, it raised questions that agencies had long avoided asking. But the most striking part wasn't the reversal itself, it was what came after. As the tail flipped, the background radiation near the object dropped dramatically. Spectrographs showed an absence of emissions that had previously flooded the surrounding space, like someone had pulled the power cord. And then, 6 minutes later, a new tail formed, thinner, faster, but this time pulsing, not flickering like before, not turbulent like a solar flare wake, but rhythmic, with a measurable beat. Researchers analysing the wave structure noticed something disturbing. The pulse aligned with the orbital harmonic of Jupiter, one emission every 9.9 hours, the same interval as the gas giant's rotation. Was 3i Atlas targeting Jupiter? The plasma wake suggested it might be more than just a destination. It was aligning, not to gravity, but to rotation, a trajectory sync that hadn't been observed in any known comet behaviour. And as this newly reversed tail continued to flare forward, it painted a narrow ribbon of particles across the trajectory path, as if marking its intention, a breadcrumb trail, a cosmic signature. It was now clear that the object was no longer just growing, it was refining. Every behaviour, every reaction was sharpening in precision, and that precision was pointing directly toward Jupiter. While attention remained fixed on Jupiter's vast magnetic field and swirling atmosphere, something quieter was unfolding nearby, on Europa. The icy moon, long suspected of harbouring a subsurface ocean, had become an unintentional sensor in the unfolding mystery. Instruments aboard a Europa-facing orbital relay began registering a repeating disturbance, not seismic, not gravitational, but electromagnetic. A low-frequency hum that echoed through the icy crust in rhythmic bursts. Every 63 seconds the same interval reappeared. It was faint, like a heartbeat under thick glass, but persistent. And strangely, it didn't match any known emission from Jupiter's radiation belts or volcanic interactions from Io. It was unique and directional. The signature appeared to originate not from Jupiter itself, but from deep space, from the vector path of 3i Atlas. What puzzled mission scientists was the medium of transmission. Space is not kind to low-frequency waves. Without a conducting medium, signals like this should have dissipated, yet the Europa relay received it clean, with minimal phase distortion. That suggested one thing: the signal was being guided, perhaps through a tethered magnetic tunnel or a field corridor aligned between the object and Europa. If so, this wasn't just passive communication. It was targeted, and the timing was just as disturbing. The signal began arriving precisely 2 minutes after the plasma wake flipped forward in the previous chapter. That meant 3i Atlas had not only reversed its emissions, It had redirected them across millions of kilometers to strike a moon. And not just any moon. Europa, one of the most likely candidates for alien microbial life. A place where water, heat, and chemistry intersect in a way we barely understand. Was it coincidence that the only moon suspected of being oceanic had become the new target of a synchronized pulse? The question grew darker as scientists noticed another correlation. Each pulse carried a modulating subharmonic, faint oscillations within the main signal, that matched tidal distortions in Europa's crust, as if the signal was measuring stress, or worse, probing it. That launched an urgent review of past data. Had any comet, asteroid, or rogue object ever sent focused frequency bursts toward a moon? Nothing in the record even came close, but some experts noted the eerie resemblance to terrestrial echolocation, a technique used by whales and bats. Project sound, measure return, understand the environment, a process of mapping. Was 3I Atlas mapping Europa? If true, this marked an unprecedented moment in observational astronomy. A comet-like object not just emitting noise into the void, but aiming, tuning, and listening to what came back. By the end of the day, more than a dozen observatories across the globe had logged into shared telemetry pools. Everyone was trying to catch the signal. Some succeeded, others failed. But the ones who found it confirmed one thing. The signal was getting stronger, and Europa was starting to respond. As astronomers continued tracking the expanding volume of 3I Atlas, one particular shift caught the attention of spectrochemical teams at multiple observatories. The presence of an anomalous gas envelope, one that did not belong to any known trajectory of solar system comets. Typically, comets that begin to expand this close to Jupiter's magnetic domain exhibit emissions of water vapor, carbon dioxide, or methane, triggered by internal heating or tidal stress. But the gas now trailing behind 3I Atlas carried a far more complex signature, an ionized compound resembling sulfur trioxide, but without the decay rate expected in such plasma conditions. It wasn't just odd, it was chemically confusing. This wasn't a case of misread data. Observatories from Chile to Hawaii, even independent amateur stations with high-precision filters, all began reporting the same distortion in the ultraviolet spectrum. It suggested a process not driven by sunlight alone, not photodissociation, not heat, release, but rather something inside the object itself, like a catalytic reaction happening under pressure with a directed output. The chemical anomaly wasn't just exotic, it was directional. Unlike the typical dispersal of gases from an expanding coma, where emissions radiate outward evenly, 3 Atlas's plume appeared biased, stronger on one side of the object, aligned precisely against its trajectory vector. That meant whatever was generating the plume was doing so with an orientation, a focus, almost like a jet. This sent ripples through the interpretation teams. Could this be outgassing? Yes, except for one problem. It wasn't stopping. Most comets release sudden bursts of gas as they cross certain temperature thresholds, venting pressure that builds from beneath crust layers. But this wasn't a burst. It was sustained, over hours, then over days. The same wavelength, the same alignment, the same chemical structure. Like a slow burn, like a reactor, theories began to fracture. Some proposed the presence of layered chemical ice pockets, trapped volatiles only now exposed. Others leaned toward a magnetic interaction that had not yet been catalogued. But one interpretation, whispered only in private briefings, made people uncomfortable. That 3 Atlas wasn't venting from internal stress, it was emitting by design, a kind of passive propulsion, or worse, communication. The spectral line that had originally appeared benign began to pulse at regular intervals, like a heartbeat, like a signal, each wave spaced with near-perfect timing, far too clean for chaotic natural emission, and each aligned, impossibly, with the orbital vector of Jupiter's closest Lagrange point. At first, teams were hesitant to go public, but then came the radar deflection shift, and everything changed. For months, ground-based radar systems had struggled to maintain consistent reflection profiles from 3I Atlas. It was distant, partially shrouded, and often too faint to produce sharp imaging. But on the morning of December 29th, something changed. Multiple planetary radar systems, including Arecibo's successor relay array, reported a sudden strengthening in echo profiles. What had previously been a diffuse return, like bouncing signals off a sponge, now came back sharp, clean and angled. It was as if 3i Atlas had rotated, revealing a surface geometry far more reflective than expected. Radar engineers typically model comets as lumpy ice rock composites, covered in uneven dust that scatters radar pulses unpredictably. But 3 Atlas now behaved like a shaped object. Not a rock, not a cloud, something angular. Its reflection came back in parallel bands, like waves striking metal plates. Not only was that abnormal, it was unprecedented. One radar technician in Canberra described the new reflection as too efficient. It had low signal loss, almost like the signal was being helped, as if it wasn't just bouncing back, it was being directed. Soon after, a separate radar site noticed something even stranger. The echo wasn't just strong, it was narrow. The beam that returned wasn't diffused like a fan, it was focused like a spotlight. That suggested two possibilities. Either 3i Atlas had an incredibly smooth surface with natural resonance features, or something on board, some form of geometric alignment, was redirecting the signal back like a dish. Not absorbing, not refracting, reflecting. This triggered a moment of alarm in the European Space Network, which briefly reclassified the object from passive to conditional active, a term usually reserved for probes or reflectors with design intent. In internal discussions, a few analysts speculated that 3 Atlas might have naturally evolved into this structure through crystallization, fracture orientation, or some kind of magnetic polarization. But others weren't convinced. The shift was too sudden, too deliberate, and timed too perfectly with the appearance of the anomalous gas emission. As one quiet memo from JPL put it, the object is starting to look back. And for the first time, teams realized that perhaps 3i Atlas wasn't just growing, it was adjusting. There's a region beyond the planets where few instruments reach, an invisible boundary between the solar wind's strength and the quiet pressure of the interstellar medium. Most objects slow here. Their tails stretch back, their radiation dims, but not 3 Atlas. Instead of decelerating as it entered the outer heliospheric gradient, the object exhibited signs of acceleration. Not in velocity, but in scale. The expansion wasn't just optical, it wasn't due to dust shedding or trailing fragments being pushed outward. The structure of 3i Atlas was growing, smoothly, continuously, and no one knew why. Juno's long-range sensors, though never designed to monitor inbound cometary bodies, began detecting subtle electromagnetic fluctuations, ones that matched the comet's previous activity during its perihelion burn near the Sun. This suggested that the growth was electrically aligned, not thermally driven. No nearby heat source, no gravitational compression, yet the object was behaving as if it were charging itself. Scientists debated whether this meant the structure of the comet was adaptive, an idea that challenged everything we thought we knew about natural celestial bodies. In normal comets, jets of gas and dust vent outward, reducing the central mass over time. But with 3i Atlas, each outburst was followed by a net gain in volume. This was particularly strange because the environment near the heliopause isn't rich in matter. It's cold, sparse, and stable. There shouldn't be enough material for any object to grow, let alone at a scale now estimated at over 760x its original form. Telescopic arrays across the Pacific began coordinating with Canadian and Chilean observatories to monitor the object's light curve, hoping to decode whether the increase in brightness was due to surface activity or internal structural shifts. The answer appeared to be both. Infrared heat mapping showed no consistent thermal zones, no steady source of venting or spiral motion. Instead, the surface began to shimmer, a phenomenon akin to diffraction, as if light itself was being twisted slightly around the object's edges. Several researchers speculated about boundary layer interference. Perhaps the object had begun warping local magnetic fields in ways that created a self-reinforcing shell. This idea, though speculative, aligned with one disturbing observational pattern. Nothing could get close. Probes launched from the Lunar Gateway to intercept 3i Atlas at high angles returned no data. Two disappeared entirely, losing signal within hours. One briefly re-established contact near Jupiter's magnetosphere, just long enough to transmit a single partial image. It showed something impossible, a grid-like shadow extending from the body's edge, not cast by light but by something else, a structure that shouldn't exist in space, transparent, precise, geometric. theories swirled. Some likened it to a Dyson skin or an artificial exoform. An outer envelope meant to modulate how the object reacted to local forces. Others believed it was organic, that the object had begun parasitically bonding with surrounding particles to grow a protective sheath. But no model could explain the consistency. No randomness, no chaos, just expansion. Smooth, intentional, like it had a blueprint. Inside mission control, the tone shifted from curiosity to concern. If this object could regulate its size in response to environmental thresholds, then it wasn't just surviving space, it was measuring it, adapting to every layer of solar influence. And now, as it approached the realm of Jupiter's gravity, the timing of that adaptation suggested only one thing. It was preparing for a transition. And transitions, especially in space, are rarely passive. The term transition structure isn't found in most astrophysics textbooks. It's not a formal category. But behind closed doors, that's what senior teams at ESA and NASA began calling Thrym Atlas. Because at this scale, with this behaviour, and with no precedent to compare against, the object had stopped fitting into natural classifications. The last confirmed measurements placed it within visual proximity to Jupiter's L1 point, a region of gravitational equilibrium where smaller objects can remain in stable orbital patterns. But Thrym Atlas didn't park, it didn't decelerate. Instead, it began folding. At first, it looked like a collapse. Telescopic imagery showed segments of the object tucking inward, curving at precise intervals. But spectrographic imaging revealed the opposite. These weren't random folds or fragments breaking loose. The curvature was regulated, like petals turning inward. Each layer wrapped over another, not to reduce the object's presence, but to reshape it. A structure that had once been elongated, tail-heavy, comet-like, was now becoming spherical. Not quite a Dyson sphere, not a shell, but a closed system. A volume-conserving transformation that suggested internal purpose. The fold zones emitted bursts of low-frequency energy. These weren't random pulses. They followed a Fibonacci-like rhythm, expanding out, then pausing, then pulsing again in decreasing intervals. Each burst matched changes in solar wind pressure. It was as if the object was synchronizing with the heliospheric current sheet, Earth's electromagnetic plane that cuts across the solar system. But here, at Jupiter's distance, such behavior had no strategic value. Unless the object wasn't aiming for planetary interaction, but for field synchronization. A kind of magnetostructural coupling with the solar system itself. A tether, one that didn't require orbit or descent, just alignment. Scientists across 3 continents revisited simulations from the object's earlier perihelion. They noticed something alarming. Each time 3I Atlas passed through a new heliocentric region, first Mars, then Earth, and now Jupiter, it shifted into a more symmetrical form, and with each transition, its mass distribution became more efficient. This wasn't just growth, it was evolution. A theory emerged, one that many still hesitated to speak out loud. What if 3I Atlas was a carrier, not a ship in the traditional sense, but a delivery mechanism, a relay station that needed to activate in specific steps, using gravity wells as calibration points? And now that it had reached Jupiter, the largest planetary magnetosphere in the solar system, it was ready to transmit. What it might send, where it might go next, whether it was waiting for a signal from us, or sending one toward another point in space, no one could confirm. But a final observation chilled mission command. In the last minute before the object entered full shadow behind Jupiter, it emitted one last pulse, not a flare, not a vent, a perfect octagonal flash, like a coded stamp, a geometric signature, one that mirrored almost exactly the patterns found in early crop circle mathematics, a language of forms, not noise, not error, but intent. And in that moment, the silence across observatories wasn't fear, it was recognition. This wasn't the end of its path, it was just the beginning of its function. As 3I Atlas continued its arc toward Jupiter, a strange distortion began to emerge in the region ahead of it. At first it was subtle, a mild gravitational haze detected in the telemetry of deep space probes and long-range radio observatories. But as the hours passed, the pattern intensified. Signals bent slightly, timings drifted by microseconds. and while the instruments couldn't yet agree on the exact cause, they could agree on one thing. Something invisible was dragging at the edges of space-time between the comet and the gas giant. Scientists initially suspected Jupiter itself. Its mass is enormous, and its magnetosphere is the largest of any planet in the solar system. It can disrupt electronics, bend solar winds, and trap moons in its gravitational web. But this time, the distortion didn't align with Jupiter's known gravitational influence. It was lopsided, uneven, and it seemed to move with 3i Atlas. Not because of the planet, but as if the comet were carrying its own field that was now colliding with Jupiter's domain. Some observatories described it as a gravitational turbulence zone, a region where the space-time fabric seemed less consistent, as though being stirred by something massive, or highly energetic, or simply misunderstood. Yet the mass of 3 Atlas, even if growing, couldn't account for this effect on its own. That's when another theory began to take shape, that the comet wasn't just reacting to Jupiter's field, it was using it. Like an aircraft catching a jet stream or a probe using planetary gravity for a slingshot maneuver, 3 Atlas appeared to be aligning itself with the natural warps in gravity. Not randomly, not chaotically, but with precision. Its tail began to bend slightly, not away from the sun, but toward the region of greatest distortion, like a compass needle twitching near a magnetic pole. The longer it stayed in this path, the more intense the haze became. And then something else emerged. Not from 3i Atlas, but from Jupiter itself. Infrared scopes detected a rise in localized heat around the planet's equatorial belt. Not atmospheric weather, not lightning storms, but internal thermal pulses, like pressure building beneath the surface, rising slowly in waves that matched the comet's distance. Some likened it to an echo, others to a preparation. Because for the first time since this object entered our system, the question wasn't just what 3i Atlas was doing to the planets it passed, it was what the planets were beginning to do in response. And Jupiter, massive and ancient, wasn't remaining still. At precisely 0240 UTC, an energy spike radiated outward from Jupiter's upper atmosphere. A clean, narrow-band burst detected first by the Japanese Hisaki satellite, then confirmed by the European Space Agency's Juno proxy sensors. The burst wasn't strong enough to be categorized as dangerous, but it wasn't random either. Its frequency mirrored a previous echo registered during 3i Atlas's solar interaction, which led to a single possibility. This was a response. For years, planetary scientists have speculated on how massive planets might naturally respond to incoming energetic bodies, whether by absorbing plasma, redistributing gravitational stress, or discharging magnetic loops. But never had this been observed in real time with a rogue object like 3i Atlas. And this wasn't absorption. It wasn't repulsion. It was resonance. The energy signature pulsed 3 times, each aligned with the comet's approach vectors. It wasn't a flare, it wasn't aurora. It was something deeper, a core-level ripple propagating from Jupiter's interior towards space. It didn't behave like heat, and didn't match any known electromagnetic outburst. It was a new category of interaction, low radiative resonance signaling. Some specialists warned against anthropomorphizing the event, calling it communication or response-implied agency. But the patterns were too deliberate to be dismissed as coincidence. The signal was narrow, modulated, and repeatable. Not only that, within hours of the final pulse, the trajectory of 3i Atlas began to subtly shift. Not a course correction, not a drift, a tilt. The entire body began rotating at a slightly new angle, as if receiving the change not from within but from beyond. It was behaving like a tethered object, one receiving directional influence from a larger anchor. Telemetry maps showed the anti-tail widening again. Spectral analysis picked up a new line in the emissions, faint but distinct. It wasn't dust, it wasn't gas. It was possibly ionic residue matching trace elements found near Jupiter's magnetic poles. Somehow the comet was pulling material into its tail, not pushing it away, and this contradicted nearly every model. By the evening, scientists from 4 international observatories submitted a joint paper proposing a term not yet used in modern comet science: atmospheric siphon interface, a condition where a moving object doesn't just leave a trail, but actively draws from the magnetosphere of nearby giants, possibly to grow, possibly to energize, or possibly to anchor. What 3 Atlas was doing wasn't travelling, it was binding. And Jupiter, through whatever deep process its gravity, plasma or magnetism allowed, was now a participant in something never seen before in solar history. An active coupling between a wandering interstellar body and a planetary field. There would be no way, would be, to stop it. Only to watch, only to wonder, what happens when this connection completes. Even now, as the sensors recalibrate and the global telescope networks realign their lenses, 3i Atlas is still moving. But we're not in the same world we were before this object approached. It isn't just that it grew, or spun, or ignited. It's that it defied almost every predictive model placed in front of it, and it did so quietly, without breaking the rules of physics, but by reshaping their interpretation in real time. The growth wasn't explosive, it wasn't a flash or a rupture, it was sustained, layered, structured, as if something within the object understood what it was doing, or worse, didn't care what we thought of it. From a cluster of interstellar dust and ice, it evolved into something far more persistent. With each kilometre it travelled toward Jupiter, its surface grew more complex. Jets began behaving like directional arrays, tails formed and then inverted. Plasma didn't just flow, it coordinated. What 3i Atlas has become is not a comet anymore. It might have started that way. But it ends as something else. As this chapter in observational astronomy closes, there are questions that now float heavier than any tale it has left behind. Why is this object only growing as it gets closer to Jupiter? Why did it wait until it passed Earth to show its full capacity? And why, of all the anomalies observed, do we feel that none of it was random? Because that's the part the math can't explain. Yes, the heat of the sun could create outgassing. Yes, gravitational lenses can bend light and stretch optical fields. And yes, objects on hyperbolic paths can appear erratic when viewed through certain spectrums. But that doesn't explain the shape memory of its emissions. It doesn't explain the synchrony with Earth's magnetotail weeks ago. And it doesn't explain the eerie regularity of the pulses still echoing through the deep space radio channels. Some say we're overinterpreting noise. Some say the data is just skewed by our fear of the unknown. But that's not how this works. Fear doesn't make spectral harmonics. Coincidence doesn't align with orbital mechanics. And growth at this scale doesn't happen by accident. Not when it's 760 times larger than it was when we first logged it. We're now in a phase of quiet waiting. Jupiter's magnetic field is immense. Its gravitational pull dominates the solar system's midplane. If there is something reactive or responsive in 3i Atlas's design, natural or otherwise, it will show up there. Not in a flare, not in a collision, but in a subtle change, an anomaly in the storm bands, a flicker in Europa's shadow, a delay in a probe signal. That's how these events announce themselves. Not like a scream, but like a whisper caught in instruments meant to measure silence. The world won't hear about it in real time. It'll happen in spreadsheets, in telemetry, in code, and only after someone goes back and looks. But the beauty of space is that it doesn't care about our timetables. It operates on cosmic patience. It lets things unfold. It allows stories to tell themselves over light years and centuries. And that's why 3i Atlas still holds our attention. Not because it answers things, but because it reopens questions we thought were closed. Where do these objects come from? Why do they accelerate near gravity wells? What intelligence, if any, is encoded in their structure? And more immediately, what comes next? Because even if it moves beyond Jupiter without incident, even if it fades into the outer solar system and becomes another distant echo in our deep space tracking logs, it will have already changed the lens through which we view everything else. We now know what to look for: the doubling patterns, the anti-tails, the directional jets, the micro-pulses. And we know that silence doesn't mean safety, it just means we haven't tuned the right frequency yet. So this isn't an ending, this is the recalibration of attention. 3i Atlas will move on, but what it awakened in the scientific community, and in those quietly watching from the edges, doesn't go dormant. We'll track the shadows, we'll run the models, we'll listen in the gaps between signals. Because once something grows 760 times bigger and doesn't break apart, once it glows in synchronized plasma while changing magnetic direction, once it survives the sun, bypasses Earth, and aligns toward Jupiter like it's always known the way, you don't forget that. You watch, you listen, and you wait, until it speaks again, because it always will, and when it does, we'll be here.